Hello everybody, it's me again. After some time not making a new video, I decided to make a new one. And right now I'm teaching dynamics class, and I just taught the tangential normal by normal coordinate, or you call it the path coordinate. So I solved the problem in class. I thought that's a good problem to also make a video and show you if you are interested in 3D dynamics. So here we have a helix with the diameter d and with the pitch of p, and there is a particle here in red that is moving on this helix, and the angle corresponding to the projection of the position vector, if you project the position vector onto the xy plane, right, then there is this angle that it makes. So let's say if I project it down here, right, and I make this, there is this angle theta that it makes with x-axis, and the rate at which this theta is changing is omega equals 6, and it's constant. So at the constant rotational speed, it is going to go up the helix. And assuming that initially it started at theta of 0, so initially it was here and now it's going up. So this was when t was 0, and now at t of 10 seconds we want to know basically what are the unit vectors of this frame et, en, and e by normal at that location, and what is the velocity, what is the acceleration of the particle in terms of ij and k. Okay, we want to know the velocity and acceleration vectors. So if you remember from dynamics, you know that at that location, basically what we have is et, which is tangent to the curve like that, right? And then we have en, which is toward the center of the curve like that. And then et cross en, which is probably something like this, is your e by normal. Okay, so we want to find these three unit vectors, also velocity and acceleration. And if you remember, velocity is only along the t direction. Acceleration can have a t component and one n component, right? We call them at and an. And so here we want to find all of this for this problem, and we're going to use MATLAB to help us. So how do we approach this? Well, in 3D, the first thing we need is the total position vector of the particle r. Clearly, if this particle has x, y, and z, the position vector r is going to be x of t, right, y of t, and z of t. And so the position vector et, if we want to basically write it, as you know, e of t is basically the derivative of r with respect to time. Okay, this is the basically vector tangent to the curve, but the magnitude of this dr over dt is not necessarily 1. But et is a unit vector, so we have to divide this vector by what? By its magnitude. If we do so, that is going to get us what? Get us our et vector. Okay, that's for et. What about en? Well, if you remember from nt coordinate, the derivative of et vector with respect to time is v over rho in the en direction. Okay, v is the speed of the particle at any point, rho is the radius of curvature at any point, and en is the normal. So clearly you see, if I divide this vector by its magnitude, which is basically this v over rho, I should get en, right? So en is what? En is clearly basically the unit vector for the time derivative of et vector, right? So if I have this and I bring it right here, that is what? That is your en vector. And finally, what is the binormal one? Well, as you know, binormal is clearly what is E binormal is ET cross EN. So these are the three unit vectors that we have, and then the speed itself, V, in this case, this radial distance R, this R here is constant, right? And what is this R here? This R here, which is the square root of x squared plus y squared, this guy is constant. And so we can say that V equals R times omega, and the A tangential is going to be R times alpha, and alpha is the time derivative of omega, and AN is going to be V squared over R. Okay, where again R is what? That square root. And once I have that, then vector V is magnitude V in the ET direction only. You know, the speed is only in the velocity is only in the ET direction, and acceleration is going to be a t in the ET direction plus a n in the en direction. Okay, now in this case, since this omega is constant, this alpha is going to be 0. So this guy is 0. But v, magnitude, the speed, and an, the centripetal acceleration, these are not constant. We have to find them at any time point. Okay, so this is all we need to do. We have to use these formulas. But the important thing is, what is this R vector? As we said, it's x, y, and z. So the question is, what is x, what is y, what is z in terms of the parameters of the helix and the time? So for that, the first thing we need to know is, what is this angle of the projection of the particle onto the xy plane? What is this angle versus time? Well, since omega is constant, clearly we can say that theta equals initial theta plus omega times t, or delta t. In this case, t0 is 0. Okay, and so this omega is 6, that's t, that is theta naught is 0, so it's simply going to be 6 times t. So this is the angle of the projection versus time. Now, if that's the case, how do we find the x, y, and z? Well, if you look at this helix from the top, right, and this is your x-axis and y-axis, of course you have to spin it. But if this is the case, and your particle is here right now, and this here is d, this diameter, d, then if this angle is theta, as you know, clearly, if you project this onto the x and y axis, you know this x is going to be d over 2 times cosine of theta, and y is going to be d over 2 times sine of theta. Okay, and theta is that function of time. So this is your x, that is your y. And what about z? Well, when you rotate one full revolution, you go up by one pitch, right? So this is the first, this is the second, this is the third, basically point on the turn, or first turn, second turn, third. So when this theta goes to 2 pi, your z goes up by a distance of p. So z is going to be whatever it was, right? When theta is increased by 2 pi, your z should be increased by a pitch. And if initial z is 0, then clearly your z is going to be what? Initial z plus what? You divide theta by 2 pi to get the number of turns, and multiply it by what? By p, and you know clearly this theta is a function of time, so your z is also going to be a function of time. Okay, so these functions in these boxes are your x, your y, and your z, and we plug them here to get my total position vector. Once I have that, I find the unit vector of it, that's ET. I find the unit vector of ET, change of ET versus time, that's EN, cross it, that's EB, and then R, I need to find this square root at any point, right? So I need to square those x and y, which is basically should be the same as d over 2, and I can find the rest of the components. Okay, so this is how you solve this problem, and let me show you how to do it in MATLAB. So this is in MATLAB. D is 4, P is 0.5, so here we just go with some numbers. Omega is 6, and here we assume that standard units, so these are like in meters, and this is like radians per second, and this is in radians. We define a symbolic parameter time, and you see this is my theta, this guy inside the parentheses, so d over 2 cosine theta is x, d over 2 sine theta is y, and theta times p divided by 2 pi is z. Combine them into a vector, that's a symbolic vector r. Now we take derivative of r with respect to time one time and take it divided by the norm of it, the magnitude of it, that's vector et. Then take derivative of et with respect to time divided by magnitude, that's en. Now we plug in the time of interest, 10 seconds, and we use the eval command to convert our symbolic variable into a number. And so that should give us a decimal for ET in terms of ijk, the same thing for EN. And then we do a cross between E and this, the order here should be backwards, ET and EN. That should give us vector EB. Also, we come here and we find R, although we don't really need R. In this case, R is simply d over 2. And v is r times omega, and then we multiply that speed by the direction et to give us the vector velocity. At is 0, an is v squared over r, acceleration vector is at in the et direction plus an in the en direction, and we also print out the acceleration vector. So let's go ahead and run this and see the results, which you can see here. This is my ET direction, this is my EN direction, and this is my EB direction. This is the velocity vector, and this is what the acceleration vector, and here these are all in terms of I, J, and K. So everything is written in terms of the Cartesian coordinates. Okay, so hopefully this video was useful to you. If you forgot how to basically do NT coordinates, or a TNB, you might call it, tangential normal by normal coordinates in 3D. Okay, these formulas are for you, so you remember them and use them. Hopefully the video was useful to you. I will see you in the next lecture. Thank you.